Good afternoon. Can you hear me in the back there? Yeah? Good. But you can't see me, huh? All right, now. All right, good. So there was a midterm 2, and you did quite well again. The mean was 85 out of 120. That's pretty good. And there were actually 5 students who had 117. And was there anything better than 117? No. Okay. So nobody 120 this time. Missed one question. Okay. So you have your iClickers with you? Okay. So let's ask you a question. Midterm 2 bonus. Everybody be very quiet, please. We talked about chirality. You should know by now, especially if you're going to be my doctor or you're going to make big discovery in molecular biology or cell biology, you should know what chirality is, okay? So we have a heptane. It has hepta, comes from 7. It has 7 carbon atoms, and I shown you some isomers of heptane. And I would like you to identify which one is a chiral isomer of heptane. A, B, C, D, or none of the above. Why don't you get started? No talking, please. Get started and give me your answer. Heptane has 7 carbons, okay? Not 8. That's heptane here. Can you read this up there? Yeah? Okay, good, thank you. E is none of the above. None of the above. Someone slipped off the screen. Only 30% had this question right. We need another 70% before I go into your office as a medical doctor. What's the answer? D. I think I agree with that. Okay, but why do I agree with this? Now let's have a look at this here. Okay, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Out. That's not an isomer, okay? Has a chiral center though, but it's not an isomer. This is 2, 4, 6, 7, 2, 4, 2, 3, 4, 5, 6, 7. 2, 4, 6, 7. Okay, these 3 here are isomers of heptane. Now, you have to have 4 different things around a carbon. This one has 3 hydrogen. No. This one has 2. 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 This one has 3. No, not chiral. Okay? Next one. This one has 3. This one has 2 CH3. Not the same, okay? So it's already out. This one has 2 hydrogen. Out. This one has 2 hydrogen. Out. This one has 2 hydrogen. Out. This one has 3 hydrogen. Out. Okay? Now, let's look at, did we do this one and this one we did, yeah? Have we done this one? No. This one we excluded. Now we're going to do this one. 3 hydrogens. Out. 2 hydrogens. Out. 3 hydrogens. Out. 2 hydrogens. Out. 2 hydrogens. Out. Now we have 1 hydrogen, one CH3, one C2H5 group here, and one C3H7 group here. Okay? Which one is chiral? This is the chiral right there. Okay? So you need to know what chirality is. It's very, very important. Alrighty? Good. So you got some extra points. Unfortunately, let's have a look at this again. Unfortunately, 34%. So we got from 33% to 47%. Not quite a big improvement. All right, so I think you will visit that question again in one of the finals or at some other possibility occasion. It will try to present itself to you again. So let's close that iClicker that we can record the bonus points. Let's close that question here. Come on. Ah, here's the answer. Good. So let's close this here. And now we go into our regular lecture. I need to start the iClicker again. Can you turn up the volume a little bit, please? So the last time, that was stuff or the subject which we discussed the last time will be part of the next midterm, okay? So, didn't I have the iClicker open already? Yes, okay. All right, too much technology here. There can't be too much technology. It's cool, technology is cool if you use it right. So we talked the last time about the kinetic theory of gases, and there we discussed or we looked at the microscopic origin of pressure and volume and temperature. So I gave you a sheet where I derived this for you, how the microscopic, or actually we should say nanoscopic, because the particles are not microscopic, they are in the nanoscale. So the nanoscopic size of these particles, how we relate them to pressure, volume, and temperature. And we found out, I showed you that P times V is, this would be the pressure here, this is related then to the mass and the velocity of that particle, and this equals RT. And with this we have seen that the kinetic energy of one molecule or one gas particle is 3/2 kBt times T, and that means Kb is a new constant. It's called the Boltzmann constant. It's nothing else but the division of the ideal gas constant R divided by Avogadro's number. So this is the energy per one molecule. So if we take this per mole of gas molecules, then it's 3/2 RT. And what you have seen here is that there is no dependence on the mass, okay? At a low temperature, small particles travel very slowly, and small particles have a higher velocity. With this, you have the same momentum transfer onto the walls, okay? So that was the first thing we learned, that there's no mass in that equation. The kinetic energy of an ideal gas is 3/2 RT, or of one molecule of ideal gas is 3/2 kB times T. And then we talked about the speed of gases, and I tried to outrun bromine, okay? It didn't work. I had a misstart, actually. The bromine actually had the misstart. And so what happened is, I would never be able to outrun bromine because we calculated that at room temperature, bromine is a Br2, has about a velocity or a speed of 200 meters per second, okay? And so if you increase the temperature, then the speed will get faster, okay? So at the increased temperature, we have a higher speed, and we have seen this then here. We calculated then. We had earlier here, we used that V bar squared, that speed, the average of that speed, and took the square root out of this. And then we get this funny expression, what we call the root mean square speed. And this is then, we have seen per molecule is 3 kb times T divided by the mass, and per mole it's 3R times T divided by the molar mass, okay? So with this you have seen that the root mean square speed is proportional to the square root of T divided by M, okay? T is the temperature. So if you plot V here and you plot square root of T here, you get a straight line. Remember, that was a chem quiz. So we have, I already alluded to this, we have a distribution of speeds. And this is given through this exponential function here. Minus E to the minus E is the energy divided by kb times T. That gives you the velocity distribution or the speed distribution. You can't read this here. This is in meters per second. So this would be at cold temperature, at room temperature, for example. Now, so the average speed, you have many of those who have a speed from here to here, okay? Now, if you increase the temperature, then you have quite a few higher speeds, okay? You can see that here. And you can also compare this if you would have a, this would be also the case where you would have a high mass, which doesn't move very fast, which gives you this kind of curve, and this would be a low mass situation. So I talked also about this, and I reminded you when we did the combustion, or not the combustion, the creation of water from hydrogen and oxygen, we needed a little bit of energy to get the reaction started, to overcome that hump of the activation energy. And to do so, we put a little flame on this, and this generated some faster molecules. They had enough speed to get the reaction started, and then they reacted, and it was a formation of a molecule. What if you have the formation of a molecule from two individual atoms? Would there be energy released? Energy would be released. That was another question in the midterm. We had potassium and fluoride, and I gave you the ionization energy and the electron affinity, and many of you calculated like crazy. But in the answer, there was only one number with a negative sign. And if you would have known, which I told you 1,000 times, not 1,000, but many, many times, if bonds are formed, energy is released. That means it's a negative sign. You just, without even calculating anything, you immediately knew that this was the answer for that question. So this is how this works, how we get this distribution of speed. So they have many more if you integrate over this, you get the same area, of course, because you don't increase the number of particles. So, and the root mean square speed is not quite at the top, it's about here, okay? So did I ask you that question? Did we get to this? Yes. Huh? We got to this, excellent. So I asked you the distribution of the speed distribution of bromine, and the root mean square speed of bromine was here. And then I asked you, this is at 300 degrees Kelvin, and so now I showed you this distribution, and I said, this is X. X can be either neon, argon, or krypton. And I wanted to know from you, what is X? Is X argon, neon, or krypton? And you've seen that the velocity or the speed here is double. It doubled in speed. So what is the equation that you would use for this here? You would use that equation, didn't you, to get that speed, the root mean square speed. So if our mass is 160, and I doubled this here, how much does the new mass have to be? 1/4. What would be 1/4 of Br2 is 160. 1/4 of Br2 is 40 argon. Okay, but this B was the right answer. Here it is again for you. That was the speed of bromine. This was the unknown, the speed of the unknown molecule or atom. And it was twice the speed. And in order to get twice the speed, you have to have a force here in the denominator. So the mass has to be divided by 4, has to be 1/4 of the mass. If you take the square root, this goes up. You take the square root of it, then you get 2 VRMS, okay? And this was so rightfully, what was it, argon. So today we're going to talk about real gases. We have talked about ideal gases, and we're going to talk about real gases and how their behavior changes compared to ideal gases. So you remember that an ideal gas, and we have this piston here, this would be our syringe, the syringe which would be closed, for example, or you hold your finger on the top, or you have a valve which you close. So at the beginning you have some gas in there, and that gas has a lot of space, and now you're trying to increase the pressure, and with this you change the volume. You decrease the volume, and with this the pressure will increase. So what you do here, you put that piston in, and there you are, and now you have the second pressure here. You see that? So you get you need a very small change in pressure. This is the pressure here, and this is your volume. You need a very change in pressure from here to here. That's the change in pressure. To get a large change in volume. You see that? Because they are still very loosely packed, these atoms or gas molecules or gas particles. So now you're going to push further in. You want to compress it more, okay, the compressibility. You want to compress it more. So now you have to push a little harder. You see that? This is your pressure here. To get this change in volume, here, you have to have this change in pressure. So you have to press quite a bit harder. And even if you want to compress it more, you have to use a very large amount of pressure from here to here, compared to the very small gain in volume decrease. Okay? This makes sense, doesn't it? This we call compressibility, and the compressibility decreases as you compress the gas. You will eventually come to a point where you can't compress it anymore. All right? So this is an ideal gas. Ideal gases behave ideal at all temperatures. Absolutely ideal at all temperatures. But this is not our reality. Our reality is that we deal with real gases. And these real gases behave a little different, because this would be, for example, the isotherm at different temperatures, so the temperature would be increasing here. So this is always true for one temperature, one given temperature. So now let's have a look at a real gas. So we start compressing it. Okay. Obviously, the pressure, that's the pressure we use, the difference between this and that, and we gain quite a bit of volume reduction. Now, we're going to keep pressing, and suddenly we feel that the volume goes in like this, without any pressure. Look at that. That's what happened. So we gained the volume reduction. No, not this here. We gained the volume reduction. See that? The volume reduced was larger here, and it's smaller here, but the pressure did not change at all. It did not change. So there must be somehow some empty space now where the gas was before. And this empty space was like a vacuum, and I could push the piston forward, and the volume changed, but I didn't have to have much pressure on there, or any pressure. What happened? You had gas, and the gas uses a lot of space. And suddenly you get another phase which uses less space. What kind of a phase would that be? A liquid. You went from the gas to the liquid, and liquids are denser. They use much less space. So the moment this happens, there's all this empty space. So the gas becomes a liquid, it has a phase transition, and this empty space is left behind, and you can use it, just push the piston in, and you don't have to do any pressure work. So now you have the water, for example, water would be steam to water would be one example. Now you have it water, now you're in a different phase. You went from the gas to this liquid phase. Now you keep pushing. Of course, liquids are even harder to compress. So now you want to compress that liquid, you need to have a tremendous increase in pressure, or you need to increase your pressure tremendously to get a very, very small change in volume, because it's much denser. If you would have a solid, it would be even more, okay? So to compress a solid is very difficult. So this is the behavior of a real gas. So real gases undergo phase transitions. Okay? There it is, phase transitions. Water, what kind of phase transitions do we have? We have gas to liquid and liquid to, and what is the solid? Ice, okay? Good. We'll talk about this a little later. And this would be, okay, now let's look at a real gas if we increase the temperature. Eventually, we will come to a point which we call the critical temperature. We come to a temperature which we call the critical temperature. Above that temperature, any gas behaves again as an ideal gas. There will be no phase changes whatsoever. No phase changes. So an ideal gas behaves ideal at all temperature. And a real gas behaves only ideal when it's above the critical temperature. And the critical temperature is for each gas different, of course. And you see then, when you come towards the critical temperature, this feature gets lost. There's no more condensation. And then you're above the critical temperatures. You see, these are these isotherms. It's a very much higher temperature. You see that there is now ideal behavior again. P times V is a constant. What the old Boyle did say when he took a break from his suffocation experiments. Okay, all right. So now I'm asking you a question. I hope you paid attention. Which is true of the critical temperature Tc for any real gas? So the critical temperature is smaller than that of the ideal gas, is equal to that of the ideal gas, or is larger than the temperature of an ideal gas? Why don't you try to answer this? I think I answered this already, but maybe you can't remember what I said to you. Can I have a little bit louder also, please? A little bit. Otherwise, they fall asleep in the back there, okay? No, I'm just kidding, okay? Everybody has this right at the first stab, huh? Because I have a big program. Get it right, please. That's a very long 90 seconds, isn't it? Yeah. So an ideal gas behaves ideal at any temperature. That's why it's an ideal gas. Real gases only behave ideal above, what's that called, the temperature? The critical temperature, okay? Why don't you try to answer that again, please? Discuss it with each other. Can I cut it short a little bit? I need the time. I have so many experiments for you. Fun stuff. Okay. I got to shave off another 20 seconds. Okay, make sure that you click in, all right? All righty, we're going to have this in the midterm. Okay. What did I say? An ideal gas behaves ideal at any temperature. A real gas only behaves ideal above the critical temperature. So the temperature for any real gas has to be larger than the ideal gas. Okay? So let's have a look at this. So ideal gases behave ideally at all temperatures, and the critical temperature is 0 essentially. And with this, you need to have it larger for an ideal gas than the ideal gas, the real gas. Okay, now let's do an experiment. So we have talked about condensation of, or phase changes of gases into liquids. Now let's do an experiment, and you could do this, for example, at your next party, but be very careful to doing this. And I know that you are not betting, so don't do that then, okay? But the other thing is, do this early in the party, because then it's less dangerous, okay? But I know that you all are not drinking, because many of you are not even 21, okay? All right, I just mentioned this, sort of. And so if I could have the camera here, please. Okay. Yeah, let's crank up the light. Is it the best focus we can do at the moment? So we are making a Coke commercial, as I see that, obviously. What's the other one? It's Coke? Zero. That's just phosphoric acid then, okay? Has nothing. Why would you want to drink it, okay? It's brown phosphoric acid, anyhow. So this is Diet Coke. We're going to use the Diet Coke, all right? So this is actually, these are empty Coke cans. And before a lecture, Karen has filled in a little bit of water. And then she put over it this glass here that the water doesn't evaporate, because Karen put it on this heat plate to make it boil, to produce steam in the can. So we have gas in the can, water gas, which is steam, all right? And then she has an ice bath here, ice and water mixture, and she will immerse this quickly, will take off the glass, and will immerse it quickly upside down in the ice-water mixture. Watch very carefully what happens, and listen. Go for it. Did you see that? The can crushed. You can crush a can without even touching it, okay? The can crushed. the can. So what happened? So there was steam inside the can, all right? And we very quickly cooled it down. And so there was then suddenly this whole volume was filled with gas first, with water gas. Now we cooled it down, and now it condensed immediately to water, and it left back all that empty space. And now the outside pressure is 1 atmosphere, and the inside pressure wasn't 1 atmosphere again. Okay? So with this, the outside pressure crushed the can. All right? So that's a good one for parties, isn't it? Be very careful. All right? I crush a can without even touching it with any force. Let's put it that way. So this is, let's talk a little bit more about, I need to give you that other overhead here, that you know what's going on. So we talked about real gases, and we talked about water already. So this is above the critical temperature. Water behaves like an ideal gas. So now if I decrease the temperature, this must be the critical temperature, because suddenly the phase transition wants to happen. And now I go to 100 degrees Celsius or 212 degrees Celsius or 373.15 Kelvin. And what will you see? That curve looks suddenly like this here. And this is the phase change right there, okay? And this would be, what do you think what that pressure would be here? The partial pressure of water, vapor. What's the outside pressure? What's the pressure we have here? 1 atm. I mean, good, you remind me, I need to get some money. 1 atmosphere, okay? 1 atmosphere, and this would be at 100 degrees, 1 atmosphere. And so that means that the water is in equilibrium with its gas, and the partial pressure above the water is 1 atmosphere of water gas, okay, of steam. And so if you would just keep just enough energy there that it would be in equilibrium, then the water would not evaporate, okay? But if you boil your water, you put a lot more energy in there that all the molecules go out of the solution, and there is no real equilibrium. So do you come back 20 minutes later and you forgot to turn it off, and suddenly you have this hot, red, glowing steam kettle there, or a water kettle on your stove. Happened to nearly everyone, okay? So like coming back to the water, so this is the equilibrium pressure is 1 atmosphere at 100 degrees. Now if we decrease the temperature to 25 degrees, then this would be, let's see what this would be, 25 degrees. This would be the vapor pressure above that little jar of water which stands here at room temperature. There is actually an equilibrium between the vapor and the liquid, the water, and the equilibrium pressure is 31 thousandths of an atmosphere, 31 thousandths of an atmosphere, okay? So you see that here. So this is also, there are partial pressures or equilibrium pressure above liquids, and I have demonstrated to you, this to you with water. So the question now is, why is that gas not behaving ideally? When we defined an ideal gas, we said these are particles, they can bump into each other, but they don't interact with each other, okay? And if they don't interact, they stay in the gas phase. But if we go to a real gas and we have a high temperature, then you have this tremendous kinetic energy, and these gas particles are not really sticking together. But there are certain forces that molecules or gas particles can have, and molecules in general, and you learned about some of those. They can have a dipole moment. Water, for example, has a dipole moment. And if you have two waters, one has delta plus on the H side and delta minus on the O side. So you have two oriented together, one the minus on one side and the plus on one side. So they will attract each other through Coulomb forces. That's a very weak force, but you have this dipole-dipole attraction. So this one will attract to here, and you have a certain amount of time where they stick together. This is when the condensation happens, actually. All right? So there are other forces. This would be with pure dipole molecules that display a dipole moment. But you can also have, for example, a gas, like xenon. Xenon definitely will not have a dipole moment, but it has an induced dipole moment. Think about it like this. You have your nucleus and you have your electrons around it, and they go in orbitals, okay? And they move around in orbitals. If you would take a snapshot in time, the electron would be here and not here. So there would be a polarization, an induced polarization for a very brief period of time. And if you have another molecule that has the same, then the negative and the positive polarized side, they would stick together. Of course, these are extremely weak forces, and this is how you can, this would be induced polarization. You see that it would be, the cloud would be asymmetric. It would be over here. This would be more negative, and this would be no. So this is the positive part. That means, let's see, there's the delta plus here, and there's the delta minus, and the delta plus, and the delta minus. So you would have some brief interaction. And then there is even a stronger interaction, and this happens with water, is hydrogen bonding. Actually, it's not bonding. It's an interaction between the positive and the negative dipole, but it's a little bit stronger interaction. It's 1/100th of a real bond, actually, but we talk about hydrogen bonding. So now you understand why you can have condensation. If you have the energy low enough, the kinetic energy of these particles low enough, they will suddenly be able to stick together and to condense. So I'm going to show this with an example to you, if Karen can help me, and we can have the camera, please. So you see here we have one molecule and another molecule. Do you see it? Here, that's where we want to be. Okay, excellent. So we have very high kinetic energy. Boom, that was very high, that kinetic energy. Thank you. So they don't stick very much together. They actually don't see each other. See that? It just pass. All right? So now, see, nothing. Now, let's try that. Okay. Okay, I give you this here, okay. Now, what we do is, now we go lower in kinetic energy. We will go very slow, okay. We take these balls, you go nothing happens there. Nothing happens there. Oh, did you see that? They are bonding together. Let's do that again. So now they cannot bump into the wall. That will decrease the pressure. And if you have many of those, then the pressure will be more and more decreased, okay? And so this is how condensation essentially works. Let's do that again. There you see, enough kinetic energy. They didn't stick together. There they are, okay? These are fantastic balls, fantastic tennis balls. They go like this, you see that? Okay, thank you, Karen. All right. Intermolecular forces are part of that phenomenon that we have a real gas behavior because there's a phase transition. All right? So remember, P times V equals N times R times T. So if we have a real gas, we observe a pressure and we observe a volume. And this would be the pressure that we observe, and this would be the volume that we observe. But the volume of a real gas is different than an ideal gas, because a real gas has really particles, and they have a volume. You can push them far together, but you only can push them so far, you never can get zero. All right? So you have to account, this is to have real behavior, this is your observed volume. So you have to take the number of gas molecules times a constant will give you your ideal volume again. So you correct the ideal gas law, you correct your real gas equation with the van der Waals equation to get ideal behavior. And so the pressure itself, that's the observed pressure, and the pressure itself is then the observed pressure we have to increase in order to have ideal pressure, because we have these interactions between the molecules which will decrease the pressure, okay? So you take this, the number, and this is the volume here, the number of particles, and there's a constant, and this is another constant. So you take the van der Waals equation, and you can look up these constants for any different gas, and then you can calculate what would be the ideal pressure and the ideal volume, and with this you can correct your observed pressure and volume. So you adjust P for the collisions and attractions, and you adjust for the finite volume of the molecules. And with this you look up, for example, helium, A is 0.034, very, very small, and B is 0.024. And you see, the boiling point is 4.2 Kelvin, all right? Above that, helium behaves like an ideal gas. So helium is essentially an ideal gas. It only if you go below 4.2 Kelvin, then it behaves like a real gas, okay? Now, CO2 or water, you see, these interaction parameters, the volume interaction parameters are not very large because you have they are small particles, so that's not a big thing compared to a big number compared to the volume that you have. Can you hear me in the back there? I feel like I'm talking to myself, okay? And so see, this is always small, but this here, this is the interaction between the intermolecular forces. These interactions are large, and you see CO2 and water, this parameter becomes rather large. So we talked about thinking, let me go back to something here. We've seen here that when we have a gas, we have the pressure and the volume, we can condense it into a liquid phase, okay? Now, this would be at one temperature, and I would like to do this with you. We keep the temperature of one gas the same, like in this room, and then we increase the pressure on a gas. And that gas will be CO2, carbon dioxide. If you could have the screen, please. The experiment would be carbon dioxide. And so what you have here, if you could show it a little bigger maybe, briefly, that I can show to the students. Okay, fine. So you have here, that's a cooled assembly, and in the middle there is a tube in there. Do you see the tube in the middle here? Excellent. This is the tube in the middle. And there is CO2 gas in there. And if you can go a little bit lower, see, keep going, then we see the mercury. Is the mercury all the way up? Okay, there's the mercury. We use that mercury as a plunger. We pump it up and put pressure on it, and there's a pressure gauge, which you see here. There's at the moment not much pressure in there, but when Karen cranks it up, then we increase the pressure on that gas. What should happen? It should liquefy. Let's have a look at this. Now let's go. Easy, easy, easy. You see the liquid up there? See the liquid? So now, see the pressure? Very good camera work. See the pressure here? Now, Karen decreases the pressure, and let's see what happens. See that? Now it condenses back into a gas. See that? Let's do that again. All right, the pressure is very low now. Watch the pressure. There comes the pressure increase. So now there will be the gas, the liquid. Sorry. There you see the liquid forming here, right on top of it. So now this is all liquid here. See that? All right, good. There it goes back into the gas phase. So it goes back and forth. It's not necessarily, you always think it goes from liquid into gas, but it also goes from gas into liquid, okay? So it goes both ways. Okay, thank you very much, Karen. And we start out right away with the next experiment while I'm explaining to you what we are going to do here. I will explain to you what we're going to do. All right. We have carbon dioxide, and we looked at the moment, I want to show you something else. The heck with it. We do it next time. We want to have fun. If I could have the camera here, please. Here, on the table, please. I know I'm jumping around a lot. Is this on here, this stuff? You see that? There you go. Now zoom in. Yeah, you're getting there. You're getting there. Yeah, it's not easy. Excellent. Excellent. Yeah, wait. Okay, a little focus, and then we are there. This is CO2. Okay? You see it now? CO2. You see it smoking? So what happens is, you go directly, and some of you, I had hoped that you can see it. You can see a little smoke coming off here. Yeah, there it is. Very good. Leave it. Very good. See it? So this goes from the solid phase directly into the gas phase. So it sublimes. It doesn't go through a liquid phase. That's why it is so nice to use as a cooling agent. When you buy some steaks from Omaha or something, which they have advertised in the magazines, you buy those, they throw in some liquid, solid carbon dioxide, and while it warms up, it cools the steaks. And when it's gone, it doesn't make that mess. You don't have that water. That's the ideal coolant, because if you remember when you have your ice chest, the ice gets to water, and then you have it all full, and you have to carry it through the house or whatever, and then it swaps over, and then you have all this mess, or the car or wherever. So CO2 doesn't do that. So you also can see that it builds up a cushion of gas underneath, of CO2 gas, and so you can play liquid or CO2 hockey. All right? CO2 air hockey, you see that? I think I'm getting out of reach here. So, and if after lecture you come by here, they will be much smaller CO2 air hockey. Anybody? Okay. All right, see how hardly any friction. It's like a hovercraft. All right, now let's go back to the lecture. And there we are with CO2, carbon dioxide. This is the phase diagram of carbon dioxide. So what I've shown to you, this is the temperature and this is the pressure, okay? Now, if we have a solid here, S is for solid, we go along here and we increase the temperature, which it automatically did. The room was warm, and so it increased the cold temperature of the CO2. So we go from solid, oh, it has to be a low pressure, from solid to gas, okay? You see that here. You can go from solid to gas, and that's what you have seen. If we have a higher pressure is here, we go from solid to liquid. That happens. Or you can also, if you have an isotherm, you increase the pressure of the gas, you go to the liquid. I've shown that to you, remember, in the experiment before. We have the same temperature, that was the room temperature, and we increased the pressure, we went from the gas to the liquid. So you can go from the liquid to the gas also. If you increase at this pressure here, for example, you increase the temperature. This is your temperature, you go from left to right, suddenly you come about this, along this phase boundary, and you have here the gas phase, here the liquid phase, and here the solid phase. But you come to a temperature, which is called the critical temperature, where you will have ideal behavior. See, there's no more liquid. It all behaves like a gas, a very dense gas, actually. It's called, and this is above the critical temperature. So what I want to show to you, this we talked about, and this we talked about. We can go from the liquid directly to the solid also. If you have this temperature and solid temperature, same temperature, but you increase the pressure. So there is this point, the triple point, where you have minus 56 degrees Celsius and 5.1 atmospheres. You have the solid, the liquid, and the gas phase all next to each other, all in one and the same reaction vessel. If I could have Karen's picture, please, now. All right, she filled this with CO2, and see there's the pressure. It should be 5 atmospheres. And if you could move it, if this is possible to move this up a tiny little, no, opposite direction. It's very, very good, thank you. We've seen that there's the pressure increase, okay? So let's see if we maybe make it less light. Maybe that helps. Yeah, maybe. So Karen warms up the CO2 till you get to the temperature and pressure. The pressure is increasing here, and there's 5 atmosphere and minus 57 degrees. You should see all 3 phases next to each other. So there's some gas. You see no, let's not do that. There's gas. Where's the liquid? The solid is here. Where's the liquid? You will see some bubbling. Not yet, not yet. You see it? Where? Here? Starting to boil. Wait, stop. Quiet. Ah, yeah, there's the gas. Where's the boiling? Is there some bubbles here? You see bubbles? Okay. And there is the solid right here, okay? So there is the gas, the liquid, the bubbling here, and the solid. All right. Ah, yeah, you can see the bubbles right there. See that? Okay. So you only can see this in Chem 1A, and only if Karen does it. Give her a hand. I see you on Friday.